Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what's up everyone? It's been nearly 3 years since we launched the TWIML online meetup, initially as a way for listeners to connect with one another and study academic research papers together. The group really took off in mid-2018 though, when I mentioned offhandedly in my interview with Fast.ai's Rachel Thomas that I'd be taking their course, and I invited the TWIML listener community to join me. That led to the very first TWIML study group, and the folks who came together for that group have become the backbone of a community that's now over 3,000 members strong. Fast forward 18 months, and we've supported each other on our personal learning journeys and a wide variety of courses from Stanford, Fast.ai, DeepLearning.ai, on Kaggle projects, and much more. I say all that to say that I am humbled by the role that we've been able to play in helping folks learn machine learning, and I am excited about the new educational programs that we're bringing to the TWIML community this year. We recently launched a collaboration to bring you the Causal Modeling and Machine Learning course and study group, which I've mentioned here before, and today I'd like to share some new details on the AI Enterprise Workflow study group that we're launching in just a few weeks. If you've been listening for a while, you know that I am very excited about the work going on in the ML and AI communities to make developing and deploying machine learning and deep learning models in the enterprise more accessible and efficient. In fact, we hosted an entire conference, TWIMLcon AI Platforms, on this topic just last fall. Until now, there have been very few formal resources that folks could turn to learn real-world machine learning workflows and deployment strategies. Our folks at IBM are working to change this, though, with the AI Enterprise Workflow specialization that they recently made available on Coursera. And I am super excited to share that we've partnered with them to host a study group for this 6-course specialization program, which I will personally be hosting. The courses in this sequence teach real-world machine learning in an enterprise environment, including applying the scientific process to understanding business use cases and structuring data collection, visualizing and analyzing data, and hypothesis testing, feature engineering and identifying and addressing data biases, selecting the best models for machine learning, vision, and NLP use cases, and using ensembles, deploying models using microservices and containers, Kubernetes, and Apache Spark, and applying unit testing to ML models and monitoring model performance in production. I am really looking forward to working through these courses, and I would love for anyone interested in these topics to join me. If this sounds interesting and you'd like to learn more, I invite you to join a webinar that I'm hosting with Ray Lopez, the course's instructor, on Saturday, February 15th at 9:30 a.m. Pacific Time. To register, visit twimlai.com/AI workflow. And now, on to the show. All right, everyone. I am here in San Diego at KubeCon, and I am with Erez Cohen. Erez is Vice President for Cloud and AI at Mellanox. Erez, welcome to the TWIML AI podcast.
Thank you very much, Sam. Great to be here.
Awesome to be chatting with you. Tell us a little bit about your background.
So I am leading the cloud and AI at Mellanox Technologies. I'm actually with the company for some time now, over 19 years. So been with the company from the very, very early days. I'm coming from an engineering background. I'm a computer engineer based out of Israel. And over the past 5 years or so, I'm focusing mostly on cloud and containerized infrastructure for high-speed networking, and obviously machine learning is a big part of it.
Yeah, now I've been familiar with Mellanox for quite a while, primarily in the context of like high-performance computing and InfiniBand and stuff like that. But not too long ago, the company was acquired by NVIDIA, who obviously has a big stake in deep learning and AI. What's the idea there?
Yeah, so Mellanox was, when we started, it was a networking company, and at the time we focused on InfiniBand, which was the new generation of networking at the time that was supposed to be...
Did I just date myself?
I'm sorry?
Did I date myself?
Yes, definitely. If you know InfiniBand, well, actually, to be honest, InfiniBand is still very much a very live technology. Just this week we have Supercomputing Conference, which is the large, gathering all the high-performance computers in Denver, exactly. And if you look at the top 500 strongest computers in the world today, a lot of them still run InfiniBand, which is the most efficient still interconnect, the highest performance, most cost effective. So it's 20 years old technology, but it's still the cutting edge, definitely. Running, in rates of 200 gigabit per second, which is phenomenal if you think about it. But Mellanox wasn't designed to be a high-performance computing company. It was designed to be a networking company that provides the best interconnect for data centers in the world. And it doesn't matter if it is high-performance computing, when you're running 10,000 servers doing some crash simulation of the universe, or you're running your telecom infrastructure, or you're running your machine learning and big data. So if you look at the essence of networking, in the end of the day, it is similar to many of those applications. You need a very low latency, high bandwidth, very efficient, and offloaded infrastructure. And this is exactly what Mellanox does. We do it in a way that it can fit a lot of different verticals. And machine learning and big data, and I will bundle them in a way together, even though they're not necessarily bundled together. But if you look at data analytics, machine learning is part of the data pipeline. And there's typically also big data because we usually work on large data sets. If you look at big data and machine learning, they have many high-performance networking requirements that I will talk probably about in a few minutes. And this is where a lot of the focus of Mellanox is these days. We're looking at accelerating networking and providing more efficient networking. And if you look at what NVIDIA does, they do something very similar in a different domain. They're accelerating compute. And so it was very natural for a company like NVIDIA, who is accelerating compute and providing a much more efficient compute with GPUs, to look at a company like Mellanox, which accelerate networking. And together, we're forming the 2 or 2.5 pillars of network or of clouds, basically, which is compute, networking, and also storage. The reason I'm saying 2.5 pillars is because there's a lot of networking in storage. So we're touching, Mellanox is touching mostly networking and storage, in a sense, the networking part of the storage. And we're moving a lot of compute into the networking. We can talk about that. And NVIDIA is focusing a lot about, the compute, the engines themselves.
Okay. So you've got a talk here at the conference tomorrow on networking optimizations for multi-node deep learning on Kubernetes. When I think about deep learning, and in particular the training phase of deep learning, I think of that as primarily a compute-bound process, compute-bound exercise. Why do we care about networking in that?
Exactly. This is exactly the point. It is a compute-bound process. And one of the ways to solve compute-bound processes is to add more compute. What we call scale out. Now, when you add more compute to distribute the workload so that it can run faster, you're hitting a networking situation. If you look at models today, models grew enormously over the past several years. It's not in several percentages, 100 or 200x the size 6 years ago. And the computation time and complexity is enormous. We see some models training takes weeks on the state-of-the-art GPUs or multiple GPUs. And the only way to shorten this time, and it has to be shortened because we need those learning phases to happen much frequently than once every 3 weeks, is to scale out. So basically we add multiple servers, each of them with multiple GPUs, and the expectation or the plan is that the more servers you add, you reduce the time in a linear manner. That's kind of our goal, right? So if it takes me 1 hour with a single server, adding 2 servers, I would love to have it in half an hour. And if I have 60 servers, it should take a minute. and you can do the math from here, right? Unfortunately, it's not that easy, just adding servers and cutting the time. What happens is that you have now a distributed problem. Moving a problem that runs on a single GPU to run on multiple GPU and multiple nodes requires a lot of synchronization, requires a lot of data that needs to go between the servers in a very efficient way. And this is exactly where the networking is really making a big difference.
Yeah, our listeners probably have heard of things like distributed TensorFlow and Horovod and other technologies that are more focused on kind of the software aspect of that and the coordination, the state, the shared state that enables distributed training. But you're saying that's part of it.
That's
but
part
not all of it.
Right. That's part of it. Now, yeah. So definitely. I mean, if you look at distributed TensorFlow and things like Horovod, which all they do is they try to improve the way the workers communicate with each other. The very kind of basic, most simple approach was to have a kind of a node that is doing all the coordination. So, you have X amount of workers, and they do training of a mini batch, a small set of the data, and then they send the information, the gradient vector to that server that usually we call it parameter server. He would gather all the gradients from all the nodes, will do some crashing of the data and distribute new weights for the different computes, and they would do that over and over again in iteration. That is a very naive implementation. Obviously, when you look at large-scale models, every node will send tens or more of gigabit per second to a single node that needs later on to crash it locally and distribute. That doesn't scale. That doesn't work, right? So Horovod and other solutions try to look at different ways of doing this, what we call collective operation. Collective operation in the sense that you have a number of nodes that are working in a collective way on a single problem, and they need to synchronize each other, right? So sending to a single server and get it back is one very simple way. And then there are other ways like rings that each send to these neighbors and so on. Those are all ways to drive the synchronization in a much more efficient way. But in the end of the day, you actually send and receive data. And you send and receive data in large quantities. That needs to be very low latency. You don't want to burden your CPUs with all this data sending and receiving. And a lot of the data that you send is not necessarily originating in the GPU, in the host memory. It is in the GPU memory. The question is, how do you send data from GPU through the network? Again, the simple implementation is copy that data to the host memory and then copy it again to the network buffers and then send it out.
Right.
That's a very, very inefficient way to do that. So
it's inefficient, but again, for a CPU-bound, compute-bound problem, rather, we're not as worried about latency. Why do we?
So think about how does it work? You do the training on a mini batch.
Yeah.
Everybody, you have X amount of servers, they all do this training, and then they do the communication phase. Now, if the communication phase is long, then, and you do those cycles hundreds of thousands or millions of time, this adds up.
It adds up.
Significantly adds up.
Okay.
I can tell you that when we use technologies like RDMA, which is an advanced transport service, or GPUDirect, which is a way to send and receive data from the GPU, we can improve the total system efficiency by multiple X's. And those systems are very expensive. If you look at a 10-node GPU system with 8 GPUs each, that's a lot of money. If you can do 2x performance, you just save several $1 million.
Or bought yourself another system.
Exactly. And this is only networking.
Yeah.
And this is what people don't realize. Actually, people do realize. I mean, if you look at all the big guys, all the hyperscalers, they all run this technology already for many years. They're running RDMA and they're running GPUDirect, and they're now looking at additional technologies that we bring to move some of the computation into the network, actually, called Sharp. We just announced it in supercomputing. It will be part of Nickel. Nickel is the NVIDIA communication library. So it will be available together with Nickel.
So we kind of talked about the setup and why all this is important, and then we've been rattling off a bunch of different technologies that play a role in here. I imagine part of your presentation was kind of walking through, that stack or the evolution of technologies. Is this a good time to drill into what is GPUDirect and RDMA and nickel and sharp and all these things?
Yeah, so the talk will be talking about the challenges that we just discussed.
Yep.
And very briefly talk about RDMA and GPUDirect as two key technologies that enable better networking. And then it will go and talk about the actual implementation in Kubernetes. So we are in KubeCon after all. And one of the things we want to make sure is we can enable advanced platforms like a Kubernetes cluster to take advantage of these technologies. It doesn't come up for free. If you look at Kubernetes, networking in Kubernetes is very naive in a sense still. I mean, it is evolving, obviously. It's a new platforms or framework, and it is evolving very fast now. You could see the amount of people here in the conference. It's amazing to see how much energy and how much enthusiasm there is here. And we, networking will evolve. What we are trying to do, Mellanox, together with partners in the ecosystem, and definitely NVIDIA is a big part. By the way, they're part of the talk. It's actually a joint talk between NVIDIA and Mellanox, is we are trying to make Kubernetes networking to be able to consume advanced network solutions in a very natural, upstream, standard, transparent way.
Okay.
This is really, and the talk is talking about mostly that. Obviously, we need to go through the concept of what are we trying to solve and what are the technologies, but we will try mostly to focus about how do we integrate it into Kubernetes, and then talk a little bit about, that will be the NVIDIA side. They're running this at scale in large clusters, and they will talk about what do you need to do in your data center in order to properly run this, and what's the best practices.
Okay.
So that will be the talk mostly.
Okay. Well, let's continue. We're kind of running through the technologies and the acronyms that we're throwing around, and then we'll dive into the Kubernetes piece.
So I just throw three different technologies: RDMA and GPUDirect. Those are the ones that we'll talk on the talk tomorrow. And Sharp, I just mentioned it. It will not be part of the talk, but I'll be happy to explain. RDMA is Remote Direct Memory Access, and this is a technology which it's a transport service, if you like. It's
been around for a while, right?
Yeah, it came from the InfiniBand days. It is a transport service, very much like TCP or UDP. I think most of the listeners at least heard about TCP and UDP, but unlike those TCP and UDP, it was designed in 2000 rather than the 70s of last decade, and it is much more advanced. It has few very important capabilities. First is the notion of read and write versus only send and receive. In TCP or UDP, you just send a packet, and somebody on the other side needs to get it and decide what to do with that. It is a send-receive mechanism. RDMA allows you not only to do send and receive, but actually write to a specific the memory address on the remote host or read from there, just like a local DMA. And that's opened up a lot of very interesting use cases for writing applications. It really changed how you write your application. This is one thing. The other thing is something called kernel bypass. In TCP and UDP, an application that wants to send and receive data will do a socket call, and then it will go to the Linux kernel or Windows kernel or whatever kernel, and the kernel will do a bunch of work preparing the packet and send it out. So there's a lot of dependencies on the kernel. In RDMA, you just, from the user space, can send and receive data directly, and there's no basically kernel involvement at all. So it allows you first very low latency. We're looking at microsecond latency sending and receiving packet versus, at least order of magnitude higher when you look at TCP, minimum. And then the fact that you don't go to the kernel and the NIC itself, the network adapter, implements all the transport in hardware, allows you to move an enormous amount of data without any CPU utilization, which means that, if anybody been working on high-performance networking, you know that you need to tweak the kernel and the CPUs like crazy to get the juice out of the network. With InfiniBand, it's not the case, or with RDMA, it's not the case. You just tell it to send, and it will send 100 gigabit without CPU. 200 gig doesn't really matter. RDMA is available on InfiniBand initially, but now it's a part of Ethernet as well. It's a standard. It's not a proprietary interconnect.
And is it available on any kind of enterprise Ethernet NIC or?
Yeah, so in the Mellanox is definitely one of the leaders in this space. We've been doing that for 20 years. These days, all the network adapters have Ethernet. I would argue they have RDMA. I would argue that Mellanox is far more feature-rich and stable.
I would expect nothing less.
Yeah, but there's the benefits of experience, I guess.
And so. My guess then is that GPUDirect is RDMA for GPU memory?
Exactly. So exactly right. So the RDMA allows you to write and read directly to memory. So the NIC can access the host memory. There's a lot of relationship in RDMA between the NIC and the host memory, and there's a lot of mechanism that allows it to be very efficient, including like an IOMMU implemented on the NIC. And
a lot of
IOMMU.
IOMMU?
Yeah, I'm sorry for all the acronym, but this is basically a mechanism that makes sure that you write the data to the right address in the memory, and that you're allowed to do that. So there's, you don't expect
like input-output memory, something unit or whatever.
This is typically an Intel component of the server.
Got it.
But the point is that if you think about it, when a remote host write to your memory of local host, this memory may be, in different physical, there's virtual addresses and physical addresses. So you need somebody to make sure that first you're allowed and you're not breaching and there's security breaches, and then that you're writing to the right place, because the physical memory kept on shifting and changing. So there is a mechanism to make sure that the memory is intact properly. GPUDirect is a co-development that NVIDIA and Mellanox did together. Actually, it started a while back. It started from the high-performance computing days when NVIDIA started getting into this space. I think it was over 10 years ago. I don't remember the exact date, but at least over 10 years ago. And basically what it allows the NIC and the GPU to be able to communicate over PCI directly, without going through the host memory. And so there's no CPU intervention, there's no copies, there's no lot of other challenges, blockers, and so on that we had before. And that really opens up a huge bottleneck that GPU networking had. All those copies took a lot of time, and they killed performance completely, and they synced up a lot of CPU cycles for that. So that is GPUDirect. It is almost transparent. There's some, because the NIC and the GPU need to talk, there's some system requirements that needs to be met on how the PCI layout is done, and where's the NIC and where's the GPU. It is especially important with the large GPU boxes. And typically in large GPU boxes, you will see that there's 8 GPUs in a box, like the DGX one, for example, and there's a very interesting PCI structure. It is not a single PCI switch that connects all the GPUs and the NICs there. There's a topology and then you need to be very careful on which NIC talks to which GPU to enable GPUDirect. But other than that, it is quite transparent for the user if they use the right drivers and applications. The last technology that I mentioned, and this is not going to be on the talk, is Sharp. Sharp, yeah. Okay. I explained earlier about the need to get all the vectors from when you do the distributed training, you get all the vector to a single location that does some crunching and redistribute the new weight vector. What if you could do that instead of a server or in a ring, do that on the network itself? So this is what Mellanox does. Basically, we, in our InfiniBand switches, and this is specifically for InfiniBand right now, we added a capability to run compute inside the network. So doing the, what we call reduction, the vector reduction, we do that actually on the switch systems themselves. And we can do that in line rate through a lot of many ports. Those switches has 30 ports or 40 ports, depends on the
So
generation.
the switch is not the adapters.
The adapter
doing
sends
the
the data to the switch.
Yep.
Each server sends the vector of the gradients to the switch.
Mm-hmm.
And the switch, let's say that it has, 30 ports, it gets 30 such streams.
Mm-hmm.
The switch will do the reduction, will get all the vectors, will do some crunching, and will redistribute that to the servers to continue the next phase of the training.
Mm-hmm.
And that allows you to open up a lot of bottlenecks.
And is the crunching that the switch is doing, is it like how configurable is that? Is it, there's the way that it does it today, or the kind of the way that, Mellanox says that it should do it, or is it a software defined thing where I can have a strategy and push it to the switch and it's going to do what I want? Is it how generalized is the compute available on a switch?
So it's a good question. One of the things that I haven't mentioned is our strategy around software. Okay. Mellanox is a very open source centric company.
Okay.
We believe the best hardware, and the software piece is all upstream first. Everything we do is upstream and not private or no black box software. We try to open up everything and have standard APIs. As part of this, for Sharp, for example, we have standard APIs that is developed as part of the RDMA interface.
Okay.
And then from a software perspective, it's just a standard API. The hardware implementation, obviously there is some flexibility, but that's, I think, less of the point. The point is that any application that uses a standard open source API can take advantage of any hardware that implements this API capabilities. Specifically for our implementation, it is flexible, but the flexibility is not exposed outside. It's exposed through those standard APIs.
Okay. So the idea then would be that somewhere between Mellanox and NVIDIA, you would identify what the strategies are of interest, whether it's Horovod or distributed TensorFlow or something else, and make the module available for the switch?
Yeah, so the way you consume this is through applications that do distributed training. Now, obviously, the market is quite active with a lot of different projects and so on. We try to focus on the most dominant frameworks. TensorFlow is definitely one of the frameworks we see for performance-oriented environments, which is the mostly used. And we work mostly with TensorFlow, not limited. We also work with PyTorch and Caffe and others, but definitely TensorFlow is where we invest more of our time. We're part of the community, the open source community of TensorFlow. If you look at the distributed implementation today, the most common configuration, it's like a Lego, you can put it in multiple ways, but if I try to look at what is common in the industry today, people will typically use TensorFlow together with Horovod and Nickel. Nickel is the distributed library of NVIDIA. It usually look at how do you do the same challenge of distributing workload, but within a server, right? In a server, you have multiple GPUs. You also need to distribute the workload between those GPUs. That's kind of a very similar way. And then when they scale out to multiple servers, they use RDMA and GPUDirect and all those technologies. So what we layer those together, Nickel, or TensorFlow, and then Nickel, and then Horovod. And the library that enables Sharp and RDMA and GPUDirect is Nickel.
Okay.
And that is something that will be available very soon. Now, it's not limited to Nickel. I mean, anybody can use that. It's an open source. Anybody, if there's somebody here in of the audience that listen and want to enable that for PyTorch, we definitely can do that. There's no problem.
And so then real quick, the Kubernetes piece of this, like we're talking about hardware and network adapters. There's part of me that says, this stuff is in the box. The kind of host operating system, has drivers for all this stuff. Like, why do we care about this at the Kubernetes level? What are the challenges there?
Excellent question. Somebody once said that advanced or very smart silicon is nothing but very expensive sand if you don't have the right software, right? So everything I said here, if you remember, is talking about how do I connect the application directly to the hardware almost, right? All the bypasses and all the acceleration. You're looking at layers that provide direct connectivity as much as possible from the application all the way to the hardware.
Right.
And when you go to virtualization or containerization, you actually go the opposite direction, right? You go and you add software layers like service meshes and all the other things you hear, SDNs and so on, that all they want to do is virtualize the network and provide a layer that completely disconnect the application from physical resources like network adapters.
So you're trying to couple the two to gain optimization, but these things are trying to decouple the two.
So I think they're not exactly working against each other. Each of them is looking for a different direction, and what we try to do is marry all the direction to something which is cohesive and high performance. So what all those SDN, software-defined networks, and service meshes and virtualization technologies are trying to do is they're trying to provide you layers of standardization, so you don't have to write your application multiple times for different hardware, and automations and all the other goodies like provision network through code, software defined, and so on. This is very important. You do want to have a controller that you set security elements, you set behaviorals, you create networks and ports, and so everything in software. But at the same time, if you add multiple layers of software, you have the flexibility, you have the features, you don't have the efficiency, you don't have the performance, which, you're kind of shooting yourself in the leg.
Right.
And what we are trying to do is we are trying to provide a high performance together with all the flexibility. So we're trying to marry software-defined service meshes and all these technologies and still allow in a transparent manner and without any compromises to run in full bare metal kind of performance. You're getting the same performance as you would get with a bare metal server in a very highly virtualized, containerized environment. This is the challenge that we're trying to address.
And so is there a solution? Is there a project
definitely.
or something that people can go take a look at? What is that?
Absolutely. So it's called Kubernetes. We're doing that as part of Kubernetes, right?
Okay, so it's going to get baked into...
In Kubernetes, we're developing a CNI. CNI is a network plugin. Kubernetes has this concept of CNIs. And we are today using a CNI for technology called SRIOV, which is a PCI technology. I don't think we have a lot of time to go through that. But that is the direction that we provide a direct connectivity. It's still not fully complete. There's more and more things that will go in, like SDN offloads and other things that today are available for, say, solution like VMware or OpenStack and other places. Kubernetes is still young, but we're working on this with a lot of partners in the open source community, where basically we want to provide the full, flexible, secure network with the highest performance possible.
Awesome. Well, Erez, thanks so much for taking the time to walk through all this stuff. Really great conversation.
My pleasure. Thank you very much.
Thank you.
All right, everyone, that's our show for today. For more information about today's guest or any of the topics mentioned in the interview, visit twimlai.com/shows. To learn more about the IBM AI Enterprise Workflow Study Group I'll be leading, visit twimlai.com/AI Workflow. Of course, if you like what you hear on the podcast, please subscribe, rate, and review the show on your favorite podcatcher. Thanks so much for listening, and catch you next time.